So chemical reactions, all chemical reactions will either absorb or release heat as the reaction happens. Reactions that release heat are probably the ones you're more familiar with. They are far more prevalent, and it's easier to imagine a reaction releasing heat. Those reactions we call exothermic. Exo, like exit, like the heat is leaving, is being released. And these reactions, exothermic reactions, have this thing, delta H reaction. I'll explain more what it means, but it is a negative sign. They'll have a negative value, exothermic reactions, for their delta H reaction. Reactions, if the reaction is releasing heat, that heat has to go somewhere. And so most of the time in this class, we're assuming that that heat is nicely getting absorbed by some nearby cup of water, for instance. But whether it's a cup of water or anything else, if the reaction is releasing heat, everything around the reaction, the surroundings or surrounding water maybe, will be absorbing heat. So combustion reactions, burning, imagine something burning, you know that that is going to let off or release heat, and whatever's near it, whether it's your hand or if you're holding a cup of water over it, over a flame, whatever is nearby is going to absorb that heat and get warmer. The opposite, reactions that absorb heat, are harder to imagine. When you touch something and it feels cold, the reason you feel cold is because that thing is absorbing the heat from your hand. So I'll go to the example first here. Instant cold packs. Inside of the instant cold pack is an endothermic reaction. That reaction, endothermic, the heat is entering the ice pack or the reaction and absorbing heat. Therefore, the surroundings, say your hand in an instant cold pack, the surroundings must be releasing heat. So whether it's your hand for a cold pack, or there are certain salts, not table salt, but certain salts that when you dissolve them, they absorb heat in order to dissolve, and you can actually feel the water getting colder. These things, endothermic reactions, have a positive value for their delta H. So showing you just a couple random reactions here. This first one is calcium chloride dissolving. It supposedly has a heat of reaction of negative 82.8 kJ per mole. Kilojoules, we've been talking about joules. These ones are given in kilojoules per mole. Simply because of the negative sign in front of that 82.8, I know that dissolving calcium chloride will release heat to the surroundings. The surroundings will warm up because they're absorbing that heat. Whereas ammonium nitrate, that's NH4NO3, when it dissolves, there's no negative sign here. It's a positive heat of reaction. This is actually the salt that's used in a lot of instant cold packs. Because it's positive, we know that this reaction absorbs heat. And I actually would be helpful if you wrote out the reaction absorbs heat. And therefore, the surroundings must be releasing heat or cooling down. So just from the sign of this number that you don't even know what else it means yet, we can tell if reaction absorbs or releases heat. There will be some sample problems, most likely, that ask you just to identify that. You're just looking at the sign. So this delta H reaction, it's called heat of reaction. Let me write that out for you. Delta H reaction, this thing. Remember, the delta means change. H, you can say heat or enthalpy, E-N-T-H-A-L-P-Y. And then the little RXN means reaction. Tells us something about a particular reaction. So for calcium chloride dissolving, this one up top here. Calcium chloride dissolving releases heat. How much heat? Well, it releases 82.8 kilojoules for every, there's an invisible 1 in front of the calcium chloride. So for every 1 mole of calcium chloride that I dissolve. Ammonium nitrate absorbs, because it's a positive sign, 25.7 kilojoules for every, again, there's an invisible one here, 1 mole of ammonium nitrate that I dissolve. So if you want to sort of summarize this, what does that heat of reaction tell us? It tells us the amount of heat that is absorbed or released, depending on if it's positive or negative, per, that's what the division sign means, per how much stuff, amount of stuff, specifically per mole of something in the reaction. It could be a reactant, it could be the product. Let's spell reaction correctly next time, but it's the amount of heat per mole of stuff that we use. And it's pretty predictable. So looking at what an example problem could look like. Here's a different reaction, chromium plus oxygen yielding chromium oxide. It's balanced and there's a heat of reaction given there for you. The first question it wants us to answer is, will the temperature of the surroundings, like surrounding water, because most of the time from here on out we'll be using water, will the temperature of the surroundings increase or decrease? In order to figure that out, I need to look at the heat of reaction. Since this is a positive value, there was no negative sign written. I know that that means the reaction, I'm going to abbreviate reaction as RXN, the reaction is absorbing heat. Simply because it's a positive value, the reaction's absorbing heat. If the reaction's absorbing heat, taking heat in, it's taking heat in from the surroundings. Therefore, the surroundings, the water, they must be releasing heat. And when you release heat, when you get rid of heat, your temperature decreases. Make sure that logic makes sense. That logic is going to carry you through so much more of this unit. You don't want to gloss over it until it makes sense. Once it does, moving on. I want to know if 18 grams of oxygen are consumed. So whether I said consumed on something on the left-hand side, a reactant, or produced something on the right-hand side, a product, that wouldn't change how I go about this question. 18 grams of O2 are consumed. It says in the following reaction, it means the above reaction. Find the heat absorbed or released by the reaction. Well, we already talked about why the reaction is absorbing heat. It has a heat of reaction that is positive. And frankly, we already know that this reaction absorbs 2,256.8 kilojoules, but that's per mole reaction is the phrase. That's if we used 4 moles of chromium, or you could think about it as using 3 moles of oxygen, or as producing 2 moles of chromium oxide. So that 2,256, depending on if we're looking at it through the lens of chromium, oxygen, or chromium oxide, we're going to end up with a different number in what I call our proportion. So we don't have a mole of oxygen. We have 18 grams of oxygen. We don't have 3 moles of oxygen. We have 18 grams of oxygen. We can turn that into moles. I know it's been a while, but grams equals moles times molecular weight. 18 grams, solving for the moles. Remember, for molecular weights, we do use the subscripts. O2, 16 times 2 is 32. But we do not ever use the coefficients. When I do 18 divided by 32 for my moles of oxygen, I'll get 0.5625. So setting up what I call the proportion, our heat of reaction tells us that we would use, or we would absorb 2,256.8 kilojoules if we used 3 moles of oxygen. Again, I'm using the 3 because it's the coefficient of oxygen. If in the question we were dealing with something besides oxygen, but we were dealing with chromium or chromium oxide, I would use their coefficient. I want to know how much heat, in this case, is absorbed. And the reason I know it's absorbed is because it's the positive heat of reaction. When we use 0.5625 moles of O2. Labeling your units here, I think, is really helpful. Kilojoules per mole of O2, kilojoules per mole of O2. When I cross multiply this, I get 3x equal to 1269.45, divide by 3. For my X value, I get 423.15. And since I did a good job labeling my units up top, I know that that means this reaction absorbed 423.15 kilojoules of heat or energy. That would be my answer for B. Then it asks this follow-up question, find the heat absorbed or released by the surroundings. There's no work to do here. If the reaction is absorbing 423 kilojoules, the surroundings must be releasing 423 kilojoules. Whatever is absorbed by one thing, the reaction or the surroundings, is released by the other, the reaction or the surroundings. Hopefully that made sense. Go try some.